want to make one final statement here. And that final statement is this. Suppose you were willing to tolerate errors. Can you achieve significantly greater than C? For example, a modern cellular voice application can tolerate,
Can you say that? Sorry.
please go ahead.
At the beginning, we have seen the erasure channel.
Yes.
There was a discussion there. You said if the error probability is not in the middle, but on each side, you get similar situations. So all messages being correct or all messages being wrong have the same effect on the channel. There was such a discussion. So I want to postulate that you cannot just get anything too large.
Yes, that's basically right. The point here is that, yeah, even if you're willing to tolerate errors, you don't really gain anything. So for instance, modern cellular voice applications can tolerate frame error rates of, let's say, PE of 10 to the minus 3. In other words, 1 out of every 1,000 frames contains an error. Above that, too many frames get thrown out and the voice sounds choppy and it doesn't really work too well. So let's say you're willing to tolerate a message error rate of 10 to the minus 3. Let's plug that into this inequality. So if PE is 10 to the minus 3, then 1 minus C over N, or excuse me, 1 minus C over R must be less than or equal to 10 to the minus 3. If this is approximately equal, then we have 1 minus C over R equals 10 to the minus 3, and therefore the rate we can hope to get, let's see, sorry, let's keep the inequality in there. If we solve for R here, 1 minus 10 to the minus 3 is less than or equal to C over R. So therefore R is less than or equal to C over 0.999. So in other words, R can be no greater than basically a tiny fraction above C. So in other words, let's say you're willing to tolerate some small error rate beyond 0, like 10 to the minus 3. This is basically telling you, well, in particular, if we solve this in general, R is less than or equal to C over 1 minus PE. So therefore, even if you're only willing to tolerate small word error rates, the maximum amount of gain you can get out of R is tiny. So this is basically within 0.1% of C. So in other words, whether or not you're willing to tolerate errors, there's really no point in transmitting faster than C. it's the ultimate limit as far as digital communication is concerned. Any questions on that? Yes.
So for an application like cellular transmission, their error rates wouldn't come from the fact that they're trying to transmit faster than the capacity of the channel.
That's right.
They would come from the fact that the message size is smaller than infinity.
That's one way to think of it. Another way to think of it is that they don't use capacity achieving codes. So, or they actually don't generally use codes that are guaranteed to have probability of error going to 0. Until recently, we're going to talk about turbo codes probably in a couple of weeks. Until recently, cellular standards didn't use turbo codes. They used other codes that don't have arbitrarily good error correction. So the errors that did occur were due to flaws inherent in the code. Another issue is, you're right, so the block lengths don't go to infinity. There's actually a really good reason for that in cellular. It's because having a very long block length means latency. So in other words, you would talk,
Half an hour later,
the person on the other side hears what you have to say. So that's actually a big problem, that information theory doesn't actually have a lot to say about that. The problem of low latency, high performance codes is quite a big one in research. So yeah, there are a lot of issues there. Another one is that channel strength changes over time in cellular. And in fact, you can be walking along and suddenly hit a deep fade, and then
just go through a tunnel.
exactly. So you don't. The problem is, if you knew exactly in advance when that was going to happen, then you wouldn't lose anything. But since you don't, you're almost certain to be dropping packets when you walk through a deep fade. Yeah, but we will address. Having said that, problems such as like the traditional telephone line communication, that's pretty much been solved. You can get codes that perform arbitrarily good as long as you don't worry about latency. And by that I mean, like, basically you have copper connecting you to the other party. No one else is using that copper, and there's nothing really changing on that line. There's no interference, no nothing except the noise. That problem is. There would be debate about this statement, but I would argue that problem is basically solved. We will talk about, and like I say, in a couple of weeks, we'll get to the state of the art in coding, which is families of codes called turbo codes, LDPC codes, and repeat accumulating codes. And those are capacity achieving forms of coding.
And when you said that the problem of low latency, high efficiency codes are still a big issue,
Yes.
isn't that a theoretical issue more than I guess?
So it's approached. I have to be careful what I say here. So it's approached from more of an engineering perspective, because it's hard to. Information theory basically deals with n going to infinity. So there's nothing natural in information theory about low latency. Once you accept that n is less than infinity, you lose all of the law of large numbers arguments that we've used to construct this beautiful building. As a result, I don't think anyone has really properly formulated it theoretically yet. In fact, for that reason, it's mostly approached as an engineering problem. In other words, given certain constraints or for particular systems, how do you do this? Let me be clear that there's a ton of work out there on that. So there are probably some very nice and interesting theoretical solutions, but probably not as general as this.
So it's more of a systematic approach towards building the systems more than it is a
Yes, I
comprehensive
think
theory.
that's what I'd say.
Yeah.
Okay, well, that's it for the channel coding theorem.